All right, now that we've talked about SN2 reactions, let's take a look at SN1. Similarly, the name SN1 stands for substitution nucleophilic unimolecular. Again, with substitution, we're going to replace one group with another. Nucleophilic means we're going to involve a nucleophile, and unimolecular means that the rate law for this reaction is going to be first order. Here we've got an example where we've got our alkyl halide, and this time our reaction is going to be done in water as the solvent. And in this case, the solvent is also going to act as the nucleophile. The mechanism here is going to be different from SN2. There's going to be two steps. In the first step, the leaving group is going to go ahead and take off. So here, this is going to be the first step, step 1. And step 1 is carbocation formation. And here, if we draw what we're going to be left with, we're going to have the following molecule. Where we have our carbocation, now that our leaving group has left. Now, you'll want to recall that carbocations are sp2 hybridized. And sp2 hybridized atoms have a trigonal planar electronic geometry. So we'll note here that we have an sp2 hybridized trigonal planar intermediate. The fact that the carbocation is trigonal planar is quite important for the next step of the reaction, which is the attack by the nucleophile. Step 2, nucleophilic attack. The reason why this is important is because when you have a carbocation intermediate that is trigonal planar, the nucleophile is able to attack from above the plane or attack from below the plane. And whether it attacks from above or below is going to determine the stereoisomer that is formed. So here, we can go ahead and draw in our molecule of water, the solvent, which is going to make the nucleophilic attack at the carbocation. And as you can see here, as products, we do end up with two products. One stereoisomer when the carbocation was attacked from above, and the other stereoisomer when the carbocation was attacked from below. All right, so as with SN2, let's now talk about a few of these key points, starting off with the rate law. The rate law is going to be the same. You're always going to have K, our rate constant, times the concentration of the reactants that affect the rate of this reaction. In this case, we have two steps. When you have a reaction that takes more than one step, the step you want to focus on is the rate limiting step, because the reactants involved in that step are going to be able to determine how fast your reaction proceeds. In between these two steps, carbocation formation and nucleophilic attack, the first step is less favorable, so this is the rate limiting step. When we look at the rate limiting step, you notice that only the alkyl halide is involved. It's just the leaving group leaving the alkyl halide. So as a result, the nucleophile is not involved in the rate limiting step. So similarly, the rate law for this overall reaction is only going to take into account the electrophile, which is why this reaction's kinetics is first order, hence unimolecular. Next, we can talk about the mechanism. As we said, there are two steps, and this involves carbocation formation. So we can say there is a carbocation intermediate. You also want to take note that intermediate is not the same thing as in transition state, right? SN2 has a transition state, but that's not a real molecule. all right? The intermediate is an actual molecule. So if you wanted, you could just do the first step of the reaction and stop and just have a test tube filled with intermediate. You cannot do that with transition state. Next, for stereochemistry, what we said was because your carbocation is trigonal planar with this electronic geometry, you can form two stereoisomers from the result of the reaction. So essentially, you're forming a racemic mixture. So we say that there is racemization of the reaction. Now, of course, this is only relevant if your starting molecule is chiral. Again, if your molecule isn't chiral, then it's not possible for you to form a racemic mixture. In terms of reactivity of the alkyl halides, again, we want to consider methyl, primary, secondary, and tertiary alkyl halides. In this case, it's the opposite of the SN2 reaction, where the tertiary alkyl halide is the most reactive. And that's because how fast this reaction proceeds depends on the rate limiting step, the formation of the carbocation. The carbocation is not very stable, so the more stable the carbocation you can form, the faster the reaction. And the more substituted the carbocation, the more alkyl groups it's bound to, the more stable the carbocation that is formed. So that's why tertiary is the most favorable and methyl is the least. Furthermore, it actually turns out that you can't even do SN1 reactions with methyl substrates or primary substrates. So you can really only do SN1 reactions with secondary and tertiary alkyl halides. And this actually makes it pretty convenient to distinguish between SN1 and SN2 reactions, because we said that SN2 reactions can only occur with methyl primary and secondary substrates, and SN1 can only proceed with secondary and tertiary substrates. Usually just by looking at the alkyl halide, you can figure out if it's going to be SN1 or SN2. The only alkyl halide where you actually have to question what type of reaction it's going to be is if you have a secondary alkyl halide. Okay, so now let's look at the nucleophile. Here we're going to want a weak nucleophile. And that's because for SN1 reaction, we don't want a strong nucleophile that attacks directly. We want the leaving group to leave first. So we want a weak nucleophile. For the solvent, again, we want to consider polar protic versus polar aprotic. And in this case, we're going to want the polar protic solvent. And that's because in this situation, the protic solvent, the polar protic solvent, is able to form hydrogen bonds with the carbocation, helping to stabilize it. All right. So that's the SN1 reaction, and you can take note of all the differences between SN1 and SN2.